Hey YouTube, today I want to go over some really cool tools you can use in LTSpice on your circuit simulations, and in particular how to use Monte Carlo and worst case simulations to improve your designs. So for today I built this little, let's call it an input filter circuit. I have my input voltage VN right here. I'm setting it, initializing it to 270 volts. And for today, let's say I have a design requirement where I need to be less than 50 volts on the circuit 5 seconds after power has been disconnected. So that's kind of what this circuit is simulating. I have a big Hagen input cap, hold-up capacitor, some filtering caps, and then two load resistors. Normally, if you're just doing kind of the back of the napkin calculation, you'll just start out like this, hit simulate and run, and you'll see that we're at about 40 volts when we cross 5 seconds. So initially you may think, oh, I'm good to go, right? And there's an important lesson here, and that is you need to account for the tolerances that are built into your components that you're using, right? So if you are using the best capacitor, you could use a 20% tolerance, and a 20% tolerance on a 500 mic, it could be a 600 mic cap, right? And instead of And to be realistic, you're not always going to see the worst case either. So LTSpice has a really cool tool built into it called Monte Carlo, and I've sort of commented out what it is right here. It's a .mc is what it would be if it was a function. You give it the nominal value of the component, and then you give it a tolerance. So we can incorporate this on this guy, and we'll say we need curly brackets around him, and then we have MC for Monte Carlo, parentheses, my nominal value, which I've already given it, and then I've already built in some of the tolerance parameters so I can easily just reference them. Let's say I buy the cheapo caps 20%, right? So tol underscore 20 gives me 20%. And I want the same thing for all the caps. Let's say I go really cheap on my bomb. So this was a 10 micro, and this guy is a 0.1. Okay, and then let's say I get 10% resistors. So and unfortunately, when you really start getting into this, the component labels just get really jacked up. But that's okay. Actually, it's going to be the same thing, so we'll just copy this guy. Now when we simulate, we see a nice little distribution based on, I believe the Monte Carlo built into LTSpice uses a normal distribution, right? So it's equal probability of getting plus X tolerance versus minus X tolerance. Or I guess it would be X over, no, yeah, X. So if we look at 5 seconds in our circuit now, all of a sudden that 40 volts is not looking too good, right? You can see that in one case we were up to over 60 volts at 5 seconds. So that would violate our design requirement. So that's a really good tool, but what if you just wanted to see the absolute worst case? And unfortunately, LTSpice doesn't have that built in, but it's not a very hard function to implement, right? So if you look right here, I built this function called WC, worst case. You give it a nominal value and a tolerance. So it syntactically it's the same as MC. And on the first run, it's going to just output the nominal value, and then on every subsequent run, it does this flat, and flat returns a number between -1 and 1, normal distribution, so you're getting half and half above and below. If it's above 0, it's going to take the nominal value times 1 plus the tolerance, right? So you'll hit basically a worst case positive tolerance, and if flat returns a negative value, you'll get worst case negative tolerance on your component. And so we're going to run that same simulation with worst case instead of Monte Carlo and see what we get. Now, right now, I think I'm set up for 100 runs, but with only, let's see, 5 components, we shouldn't need 100 runs, right? Some should overlap, but it's quicker just to do this. Cannot find model WC. Uh-oh. So, okay, so just to reiterate, I had a syntax error in my my declarations here, but Monte Carlo gives you a nice output of what you're probably actually going to see when you pick these components, right? It's going to have a distribution. There's a probability that you're going to be above, below, and in between that tolerance value that the manufacturer gives. Worst case is really good to ensure that the Monte Carlo captures that worst case scenario of everything stacked against me in this scenario. What is the worst possible design for, what is the worst possible scenario for this design for this particular issue, right? I want to get below 50 volts in 5 seconds. And so this should now tell me with 20% caps and 10% resistors what I'll actually see worst case scenario. And so, and like I said before, I didn't really need to run 100 runs. Obviously there's only 1, 2, 3, 4, 5, 6, 7 cases, which makes sense. And at 5 seconds, the absolute worst case scenario is about 62 volts, 61 volts. So I said, okay, that makes sense. What happens when I pick, let's say, I don't want to be cheap. Let's go to 10% caps, but I'll leave 10% resistors. How does that affect me? Just in my head, this big monster cap, this 500 micro right here, is probably doing most of the damage to my timeline. So let's see. Did that get worse? No, okay. Okay, so we brought it down a little bit, but it's still not very good, right? At worst case, it's still above 50 volts. We're probably at 54. So I say, fine, I'll go to the 1% resistors. My components engineering guy screaming, the procurement guy screaming, they're all mad at my BOM costs going up, but hey, I need to meet my design. Syntax error. Tall, oh, I called it, yeah, 01, not 1. The error messages in LTSpice aren't the best. You kind of just got to figure out what went wrong. And look at that. Now I'm under. So we can push this out. We don't need to go to the 0.1s or the 0.01 resistors. We're good. So that was just a really quick and dirty demonstration of how you can use worst case in Monte Carlo simulations LTSpice. Thanks.